Hello everyone, welcome back. Hope you had a lovely little coffee. We're now going to start with session 2, part 2. We spent the last session focusing on the impact of material provenance and how that can inform our decision making. Now we want to focus on the practical responses to some of that information, and we've got some industry leaders showing incredible innovations of alternative and novel materials. So I'm first going to introduce Julian Shepherd from Bureau Happold, and he's going to present on exploring new materials.
Thank you. So to start with, just a slide showing some of my projects, which of course I'm very proud of. Mostly concrete and steel, some timber. So that's my experience as a director at Bureau Happold. But really, my curiosity around structural materials has led me to this question. And you might want to ask, well, why arable? The reason for that is that I believe it's a safer bet when we want to find materials that we allow the sequestered carbon if we lock them into the building. So the graphic kind of shows a bundled, if you like, a diagrammatic design of bundled natural arable crop, which combines both structural and thermal. So what are the drivers for change? There's going to be lots of construction in the next few decades. We know that population growth is going to rise to 9.5 billion by 2050. At least that's a projection. So that's around about the size of the UK, the population of the UK every year for 25 years. Most of that's going to happen in developing countries. So how can we, as structural engineers, use our skills to tackle low and medium rise? Because there's going to be a lot of it. This graph shows our embodied carbon of our building designs over recent years, and it does show that we are quite a long way off the mark, the target being the dashed lines at the bottom. There are some encouraging projects. There's some neat projects down there that we take learning from, and the trend is generally downwards, but it's very slow. So how do we design for low carbon? Well, this is a carbon route map put together by my colleague Jonathan Roynan. It's on the iStrike website. It helps us understand how we can use the materials that we currently have to lower our embodied carbon. It's really good. It's worth a look. But even with the best structural design using the materials that we currently have, we're still looking at quite significant carbon emissions. Around about Engineers Declare, which was 2019, we started to strengthen our links with academia. For me personally, that was with my local university up at Bath. I set up a research pilot whereby we suggested dissertation titles for students and then supervised those students. We also set up a facility for employees to undertake PhDs, which has gone very well. And I do believe that industry and academia need to work together to tackle climate change. At the same time, I decided to reduce my hours, started working part-time working for a number of reasons, but one of them so that I could explore natural materials. So what are those natural materials? Current options, we've all heard about them: rammed earth, coppice timber, natural stone, unfired clay bricks. There are others, and we should be pursuing these. But even these have a carbon and biodiversity footprint. And then when we look at timber, I've just been having an interesting conversation with timber. about whether we can include the sequestered carbon in timber. Our approach is that we don't include sequestered carbon, but I know that it's a topic for debate. If you haven't already read Will Hawkins' report on timber and carbon sequestration, it's really good. It's worth a read. It's on the iStructure website. And then when we look at regenerative design, that steers us to ask this question, well, how do we regenerate climate and biodiversity loss? How can we reverse that? Not only reduce, how do we reverse that? That's a hard question, but we have to try and find solutions. Most of our materials are in the bottom left quadrant, even the green and sustainability movement. If we take those approaches, we're still in the bottom left quadrant. How do we move up into the top right quadrant? And my interest, if we just look at materials, what materials might occupy that top right quadrant? I think plant-based materials are the obvious answer to that, and so that's been my focus in recent years. So what are the precedents that we can look at for plant-based structures? The Iraqi marsh Arabs, amazing parabolic structures using reeds for thousands of years, really interesting. And then other indigenous communities around the world, South America, Peru, have similar structures using reed, Africa. And then more recently, we see these structures using canes and bamboo, and of course we all know the Ark project, but bamboo isn't naturally durable. So how about the crops in this country that we are familiar with? Of course we know about straw, but we can't really take straw as a serious contender structurally. And then of course there's been a lot of interest recently in hemp, and quite rightly so, but it's quite soft, and actually under sustained load it strains a long way, so it's not really going to give us the answers that we need. So miscanthus, this is the material that I've been focusing on. It's growing in popularity in the UK. First came to the UK probably 20 or so years ago as a biofuel. More recently as a growing market as it being used as animal bedding. Chopped up and used as animal bedding. And as I said, this has been my focus, and hopefully will be my focus for the coming years. So what is it? So this graphic just looks at a comparison with bamboo. So a small stalk of bamboo. So bamboo is hollow in the center. It has this outer timber-like structure. It's strong. It's not durable. Hemp is insulating, it's not strong, it's not durable. Miscanthus kind of combines the two. It has this outer cylinder of timber-like structure, so it's hard, and it has this inner shiv-like insulating material, and it is durable. So it grows to around about 2.4 meters in this country, 2.4 to 3 meters-ish. And around about 1.8 meters of that is usable, i.e. it's hard. The top section is quite soft. It's part of the C4 photosynthesis group, which means that it photosynthesizes almost twice as fast as other plants. It's a coppice crop, which means that the rhizome roots stay in the ground. Every year it gets harvested, and those sequesters carbon into the ground as well as the stalk. And then next year, the crop grows from the rhizome roots. In cross-section, it looks like this. The stalks are around about a centimetre or so. And you can see there in the graphic, there's a kind of green outer leaf, which comes off quite easily. And then you're left with a timber-like outer cylinder. It looks very similar to bamboo. In fact, it looks identical to bamboo. But inside you have this insulating shiv. University of Aberystwyth had done, about 5 years ago, investigated miscanthus, which is great, and they wanted to prove it as an alternative to hempcrete and straw bale from its insulating properties, and they certainly did that. Images there on the left and right. So it can be used as an alternative to those materials, but for some reason, I don't know why, they didn't explore combining its structural strength. And when I spoke to B. Rowan, who's an expert in straw bale, about it, 'cause she worked on that project, she said, "Oh yeah, it's awful stuff. It's just far too hard. Every time you walk past it and you brush your leg, it cuts your clothes." And I said, "Oh, actually, that sounds quite good to me." So perhaps we could use that structurally. There are some good historical precedents of its use. The Japanese have been using it for thousands of years as roofing thatch. Also, Japan has a damp marine environment similar to our own, and it's very good in damp conditions. It has enough lignin and silica in it to make it naturally durable. So around about this time last year, I set about harvesting some miscanthus to play around with it, and found a miscanthus farm about 7 miles from my house, Wadswick in Corsham, Wiltshire. And they were very happy for me to have some, although puzzled as to why I wanted it. And then I went about drying it for a few months, and thanks to my wife and kids for allowing me to lay miscanthus out on our underfloor heating. So we dried it and tested it in actually my greenhouse to begin with, just some fairly rudimentary tests. And so this shows the test of 8 upper stalks and 8 lower stalks, bound together with polypropylene confinement, tight, just to understand whether we can I could transfer the load through friction, and managed to hold a kilonewton of load on the 8 stalks before it started to slip. So that kind of gave me confidence that, okay, this potentially is a material that we could use. And so then I suggested it as a dissertation topic, going back to the Bath University link. And so the dissertation student, I took some tests with my supervision. This is just one of the tests. So this is just a simple single stalk. You can see the wood-like fibre at the top left, the failure. We managed to generate 3 kilonewtons of load, which is actually quite a lot of load. And when you spread that over the wood-like outer cylinder, that equates to around about 50 to 75 megapascals. So actually it's quite a high stress. And then we also did bundled tests, and these weren't successful. Well, only in that we realized actually each individual stalks were buckling individually, and the sizal confinement that we were using just wasn't doing the job of helping those stalks to work together as a whole. So somehow we needed to improve the interface friction. And then this summer and autumn, in fact only very recently, we've run some more tests, and we spent a few months trying to work out how to improve the confinement. We came up with a tensioned wire system, works really well, digs into the wall of the miscanthus on the outside and really compresses the bundle. So that works really well. And we also wanted to include sharp sand inside between, in the interface between the stalks. And obviously we needed to hold that sharp sand in, so we used a binder. We used 3 different types of binder: clay, lime, and cement. And we undertook three tests, 3 basic tests. The first one was direct bearing, just stalks from top to bottom, again with sand binder within. And the second test was a friction test. So we had a bundle at the top, bundle at the bottom, interlocking, so the load transferred through friction, through the sharp sand and the confinement. And then the third test was just a simple end-on-end bearing with a sand cement plug. These are the test samples, and these are the results. So on the left-hand side, we have megapascals. X-axis is strain. Solid lines were the direct bearing tests. The dashed lines were the friction tests. So as you can see and expect, the solid lines, the direct bearing tests were obviously better. The dark black lines are using cement binder. We're not serious about cement binder, but we wanted to use it to try and get a feel for how the strength of the binder changed the result. And all of the tests failed in buckling, and actually that was quite encouraging, because what that means is when these bundles, you can imagine them being part of a building, part of a wall, the fact that they're joined together adjacent to each other is going to increase their buckling resistance. So these stresses, allowable stresses, will probably increase. This graph just takes away all of the cement and lime binders and just looks at no binder and clay binder friction tests. So the reason friction tests are important is because we know Miscanthus doesn't grow tall enough for us to use just a single stalk spanning the full story height. So we know we're going to have to transfer load somehow, either through friction or end-to-end bearing. So this is an important result. And so what this shows us at the bottom line is the no binder, just straight Miscanthus with a simple confinement wire, and we ended up achieving 1 megapascal. Adding the sand with the clay gave us a 3-fold increase in stress, which is really good. But taking the clay out and just improving the confinement, we were able to improve by four times. So that showed us that the confinement was super important, and the clay is worth including. Sorry, clay and sand, worth including. So let's just put that into context. What does a 2 to 3 story resi building, how much stress would that kind of building put on a 300 millimeter wide wall? And actually it's quite small. It's very small, around about 0.1 megapascals. So actually these the loads that we were getting out of Miscanthus are way in excess of the kinds of loads that we would expect, which is good. Just again, putting it into context, a rammed earth is around about 1.5, considered to be around about 1.5 to 2 megapascals. So the line at the top there is double that. So not bad. We also did thermal conductivity tests, and the result of that is that actually, yes, pretty good, as we expected. Very similar to straw bale and hempcrete. So, in summary, it is a potential material for structural use in the future. Obviously, there needs to be more work done. It has good thermal resistance. It has very good inherent durability. And we can use the sequestered carbon because it's an annual crop. There is more work to be done. So the next steps, first of all, I need to secure funding for the next stage of the project. And we'll be doing more tests, bending tests, tensile tests, and also looking at the buckling resistance. And we also plan to construct exploratory structures. There we are.
Thank you, Julian. I think that presentation is really inspiring in the sense of how your personal curiosity in a material has allowed you to explore it and actually developed an innovation. So we all have to have that little curiosity and exploration in our work as well as engineers. So on to our next speaker. Annalisa presented us the issues of the wider landscape and responsible timber sourcing. We're now going to take this back home with Tom Henderson from Wood Knowledge Wales, and Tom's going to cover how we can create local supply chains in the UK.
Well, hi everyone, thank you. So, is this on? I'm Tom from Wood Knowledge Wales. So if you don't know about Knowledge Wales, we champion timber. We're all about timber and getting more of it into the built environment. I think we're all here collectively in agreement, apart from one of us maybe, that timber is, it's a ready avenue for sequestering carbon in the built environment, and we're exploring its role as a GGR. We're all here because of the climate, and I'm here to talk about timber and where timber fits into the sort of the climate story. So we know timber's got massive potential. What's not quite as tangible is the sense of place that's associated with timber. Timber comes from forests, so when we talk about timber as an industrial material, it's sometimes easy to get, you fall into this mentality of thinking that timber comes from a catalogue or a warehouse, but it doesn't, of course. It comes from a forest. Forests are dynamic, living things, we believe there's a real bit of a disconnect in there. Today I want to explore understanding provenance and how understanding provenance can help us sort of close some of those gaps and make some of those links between our forests and how we manage them, and then how we use the timber as well. So timber, a green resource, it sequesters carbon as it grows. We cut those trees down, the carbon doesn't go anywhere, it stays in the tree. We build things from those trees and the carbon is stored. There we are. But moreover, timber's a vital part of a wider system. So it's not just part of the building system, but it's part of the forest, which makes it part of the cultural system and the wider ecosystem within which it's embedded. And again, just to come back to it, we can see lovely bits of timber here, but as soon as it's in an application or as soon as we're looking at it in a catalogue, the sense of place is kind of stripped away by that almost. Despite all of this, we do use timber in construction. We do use timber in construction and housing quite a lot. In Scotland, as high as 90%. So 90% of new build houses in Scotland are built from timber. In England, it's a bit lower, it's about 9%, and in Wales, it's about 22%. So we do use some timber, well, we do use considerable amounts of timber in the built environment, but very little of what we produce here makes it into those sort of long-lived, high-value structural uses that we'd like to see it go to. And in this story, you guys have a hidden superpower. I should say, by the way, I'm a conservation forester, so this is a totally alien world to me. I know nothing about structural engineering, nor am I an industry leader, although I am flattered. But I do prefer the term master student. But so there's a definite disconnect, and we believe you guys have the power. So we can grow the trees, and we can research forest ecology and carbon dynamics till the cows come home, but there are gaps in this supply chain that require us all to work together, and that's what I'd like to encourage us to do. So a lovely picture of a forest here. This is the start of the timber supply chain in the UK, and this is a pretty typical forest. I don't know how many of you spend a lot of time in forests, but this is what productive forestry in the UK really looks like. So we've got, this is a forest near Llandegfan, just south of where I live. These are productive conifers on the right. So these are Sitka spruce, Douglas fir. When we talk about timber in construction, this is generally what we mean. We mean coniferous trees. They grow faster, they grow straighter. Over here, in our typical woodland, we have a broadleaf component. Now, this isn't the sort of timber that we're used to in the built environment, and it isn't by accident either. So all forestry in the UK is governed by the UKFS, that's the UK Forestry Standard, and that's a sort of quite an extensive list of rules about what you can and can't do, and guidance about what you should and shouldn't do. And it applies to every forest in the UK. So if I can dispel this rumour straight out the gate that plantation forests are ecological deserts, then I'd like to do that. This is what it looks like, and I know because I took that photo. So the UK Forestry Standard, I should say, gives us a baseline as well. So the UK Forestry Standard is all about making sure that sustainable forest management, I'll just go back to that slide. The UK Forestry Standard is making sure that sustainable forest management incorporates this element of timber production. So we're getting material out of the woodland, but it makes sure that it does it in line with other goals. So this could be ecological goals. You can see a track here through the middle. Recreation is a massive part of UK forestry. Foresters are always encouraged to open the woodlands up wherever possible. And what these woodlands are doing in their place in the landscape is they're doing lots of wonderful things. So we all sort of assume that timber is a good thing, in the same way that we all assume biodiversity is a good thing, and it is. But it's actually quite a complicated relationship. So this is an ecosystem comprised of living and non-living components. Non-living components being topography, geology. Now the biodiversity is the living component of this system. It is not necessarily valuable in and of itself. There is a bit of cultural value associated with biodiversity, but the real value to society of these systems is in their ecosystem services. That's the services that we as people receive that increase our well-being. So this is things like carbon sequestration. This affects everyone all over the world, no matter where the tree is. It stores carbon, it reduces atmospheric carbon. And we've got some more localized benefits as well. So forests actually slow the water that falls. Forests slow rainfall down, which does two things simultaneously. One, it can alleviate flooding and attenuate stormwater. And other than that, it actually increases the amount of water that percolates into the ground. So what we get, the water that comes off forests is filtered mechanically as it moves through vegetation, and it's filtered chemically as it moves through the soil as well. I could go on, but I won't. Yeah, forests are brilliant. Yeah, so timber as an industrial material. This is the interface of our worlds. This is where we sort of connect and where we can really make things happen. For timber as an industrial material takes forests out this world of sort of esoteric, poetic beauty, and it grounds it in the realities that we face, that you face as structural engineers. Our forests are already impacted by climate change. That means our forests are already impacted by the things you do. Whether you spec timber or whether you spec concrete or miscanthus or whatever it is that you specify, that has with it associated environmental burdens. They impact the forest. What happens to our timber is decided in markets. We'll talk a bit about that as we go along. And what we think is required here is some demand side pull. So what we're saying is that we do grow lots of timber in the UK, but we don't use it properly. We'll explore this as we go on. So where does our timber come from? Well, as we've already talked about, we import 80% of our timber. It's an astronomical amount, second to China, and Alisa told us earlier on. Most of it comes from Northern and Eastern Europe. These parts are sort of parts of the world are dubbed as the world's timber supermarkets. As you can see, most of it comes from Sweden, Germany, Latvia, Finland. Now, the climate there is a little bit colder, and generally the forests are a little bit higher up, which means that their timber grows slower. It takes about twice the time to reach the same height as the same species would here, spruces, firs, that sort of thing. Now, there's some misconceptions about its strength and what that does to its strength. The slower growing means that the tree grows less as a youth. So essentially, it has got a smaller juvenile core. Now, this juvenile core makes the timber unstable. So the difference between C16 that was mentioned and C24 is not necessarily strength, it's stability. The colder climates in Europe produce high quantities of C24 grade spruce, whereas we do C16. The key point here is that the future of this supply, the world's supermarket for timber, is looking like it's about to close its doors very soon. Like I said before, climate change impacts forests the world over, and all of these big countries that we see here are now massively affected by drought. They're massively affected by increases in temperature, which invites pests and disease. So anyone who's tried to source timber from Europe recently knows that there's an infestation of ips, which is a bark beetle, which has absolutely decimated a lot of the forests in these regions. And what we're seeing is sanitation fellings. So the forests are threatened by pest and disease, so the forester will go in and remove all the timber preemptively so that it doesn't get diseased. So the future of these forests is precarious. What about our own forests? Well, we produce quite a lot of timber, 10 million tons of timber, which is quite a lot. we use about 6 million meters cubed, for reference, in the built environment in the UK. So technically we could do it. We do produce enough timber to supply our own construction demands, but that's not what happens. So this is a Sankey diagram, which is a bit of a rough estimation of what happens to timber that comes out of our woodlands. So we harvest it, about 60% of it goes to sawmills, a lot of it goes to energy, bioenergy production. Once it gets to the sawmills, it's sorted between green logs, red logs. But essentially what happens, by the time you get to the end, it's only 8.5% of the harvest ends up as structural building material. Most of what we produce in the UK goes to fencing and biomass. And now there is a reason for that, and essentially the reason is because timber is a global commodity product. So we can explore that a bit more. Let's stay on there, sorry. So timber's traded as a global commodity, which means that the breakouts from the sawmills, the products that they produce, are ultimately decided in markets. If a large sawmill who process 90% of the timber, so if these large sawmills decide that there's a market for something, they'll produce it. It's as simple as that. So we can see that they seem to think that the market is for fencing and for pallets, and that's true. Now, the reason for this, sorry to go back and forth a bit here, the reason for this is because of the large quantities of C24 that are coming from Europe. We're growing vast quantities of it, and the sanitation fillings are flooding the market. So as Europe change their forestry, it requires that they cut a lot of their forests down because they're under threat. That floods the market with C24 timber, which makes our C16 timber, which is about a similar price. It makes it not less attractive to you guys. But the central message of this really should be that we need to remember that the wood that we spec comes from a forest, and it has embedded in it an ecological legacy, and it also sends signals that will influence the next ecological legacy. So the products that we use our timber for define the value of that timber and essentially support forest management in the first place. So we reached out to some structural engineers and we tried to work out what do you guys think? Why don't you use timber in the built environment? And these are just some of the questions or statements that we got back. The first one: we don't grow the kind of timber that you can build with in the UK, which is something I've kind of heard. But that's not true. We produce C16. Now, Timber Development UK, just this week, before I had a chance to update this, actually announced that they've unveiled a new campaign for C16. So Timber Development UK are convinced of the properties of C16 and that it's more than suitable for this sort of low-rise, mid-rise construction that we do here in the UK. So it's not that we don't grow the timber, we don't use it. Timber is old tech and low-fashioned, and I think this uncovered a sort of deeper perennial issue in sustainability, is that we tend to err on the side of innovation. There are a lot of timber building methods, which at one point were called modern methods of construction, but the systems are in place. We know how to build with timber, so we think there's a bit of a warning. Sometimes these highly advanced systems are a bit of a red herring. It's actually about rolling out what we know we can do. Timber framed houses are unsuitable for the UK climate. This is an interesting one because I heard earlier on someone mentioned moisture. Now, this, I'm assured by my structural engineer colleagues, comes from a whole bunch of houses that were built after the Second World War, which were structurally unsound and unfit for purpose. And it created a lot of fear about fire and fire resistance. Now, we know that timber actually chars where steel will melt and bend. So I think that the fire resistance claims have been quashed. But now the questions around timber suitability are around moisture. But we think that the fact that insurers are now worrying about moisture and not fire is progress. Moisture is a real issue that we need to deal with. Fire is not so much. And finally, shouldn't we only plant native broadleaves to help nature and the climate anyway? No, in short. So this goes back to that picture of the forest together. What we think is, because timber and sustainable forestry in the UK is mandated by the UKFS, and we know it's going on, It offers an opportunity for a more integrated approach to sustainability. It's not about offsetting and offsetting the damage somewhere else. It's about developing integrated systems and a more holistic approach to sustainability. So we have to get comfortable with building with timber. Rather, you have to get comfortable with building with timber. Sorry. The engineers we spoke to said they felt it was a far off and mystical material, which is wonderful, and I agree, it is mystical. But far off, it is not. Like I say, sometimes we're misled by some pursuit of some innovation where what we have will do just fine. The industry is upside down. It designs first and looks at sourcing materials after. I can't speak to this because I'm not a structural engineer, but I'm hoping this just, if you can come away from this with one thing, that's what I'd like you to think about. We talk about material resource scarcity, and not all timbers are created equal because of ecosystem services. Where the forest is has a massive impact on the benefits that people receive from those forests. So we'd like you to consider that and to start with what we have. Start with what do we have and then try to design systems that work with what we have. So this is about building with C16 and not just speccing towards C24. Just this morning, I've seen a coffee table stand with C24 printed on it. So it's again, another perennial issue. Yeah. Ultimately, we think that the barriers to C16 are about perception. It's not about the structural integrity of C16. It's not about producing C16 domestically. It's about the way that designers and the people who specify timber perceive UK timber. And we are working, and Timber Development UK are working to change that as well. So what can we do? I'll gloss over a bit in the interest of speed, but we think there's a real gap for skills, training and education. We think that timber needs to be a more fundamental part of structural engineers' education. A lot of the conversations we had were the first conversations that the structural engineers had about timber in a serious professional context. So something we can do to move towards using more C16 is growing relationships. I talk about the big sawmills, and the big sawmills put all of our timber into pallets and packaging, which is true, but there's another side to the story. There's a constellation of small sawmills in the UK. This is, a guy with a saw bench or a guy who employs his son. There's a lot of this. It's kind of shed industry stuff. But what they do is they know every tree in the local forest, and they'll liaise with a client a lot of the time. And it creates this sort of shortened, usually for bespoke application, but this shortened supply chain. And we think something we can do pragmatically and practically is by nurturing those smaller processes from the ground up. We can't expect the big sawmills to change their output overnight because they compete with global commodity markets, but we can nurture the small sawmills. But that means building relationships. These guys don't have websites. You've got to go and know. Yeah. Okay, so just to kind of finish off, we are doing quite a lot, and it's not doom and gloom. It's very easy to look at those big mill stats and think, well, what are we going to do? But we actually do produce some engineered timber as well, cross-laminated timber. These are sort of mass timber engineering solutions I'm sure you know all about. So we are now producing British CLT from British logs. That's actually helping us deal with the larch crisis as well, which you can ask me about. Corwin Sawmill, just another example of a sawmill, that small family-run local business who are investing in secondary processing machinery that allows them to access construction markets. Okay, and far be it from me to tell you all how to do your job, but and if you'll excuse the crude diagram, this is what we're trying to get to here. At the minute, it seems to us that we're designing for what we want, then we're specifying for the materials that will fit that purpose, and then we go looking for them, and it leaves us open to all sorts of, well, a precarious position. However, we have a vast network of forests in the UK, and the timber is criminally underutilized, and we think just a sort of simple shift about looking at what we have, looking at what we need, and drawing the arrow that way might, yeah. So Great. And yeah, that's the first time I've delivered this presentation to a bunch of structural engineers. So thank you for bearing with me. And look at the lovely words. Thank you.
Oh, that's great, Tom. Thank you for delivering that to us structural engineers and giving some really actionable insights for us to all take away. Now we're going to take it back to the material that unfortunately we all can't live without, concrete. So we've gone from scanthus to timber and we're bringing it back to concrete, the material, something that we can really take away and action on our projects. And we're really delighted to be joined by a structural engineer and also a developer, Jonathan Lee from Canary Wharf Group, to share some of the practical insights and solutions that they're developing on the Canary Wharf estate. Over to you, Jonathan.
Good afternoon, everybody. Yeah, it's a great pleasure to be here. So as you can see, I'm a structural engineer, but I also work for a developer who happens to have a construction arm as well. So it's quite an interesting dynamic to work in this organization where we've been able to be very adaptable to picking up on ideas and trends and seeing how we can implement that through to our projects. So one of the key things about bringing ideas to the forefront of projects is the collaboration, and we've been able to establish some great relationships with our supply chain. And the images here shows a site visit that we arranged for our graduates for a lunch and learn session at one of the concrete plants that was local to Canary Wharf. And it was by chance the grads noticed this operation in one corner of the batching plant, and it was these big heavy machines crushing waste. So the curiosity in the group asked, well, what is it that you're doing? Could we learn more about it? And what they were doing was that they were saying they were generating recycled aggregate from waste. So because of the group that we had, we were working on a project where we were demolishing a lot of concrete. So the idea of being able to connect people together to generate positive outcomes is a key to unlocking future ways in which you can decarbonize and design things more sustainably. So it's about seizing the opportunity. So I mentioned the project that we were demolishing. What that project was an existing false quay. As you can see there, the historical photo shows it being there for over 100 years. But unfortunately, we had to make way for our new development because obviously we were constructing a 23-story tower, which couldn't be supported by the existing false quay. So as you can see there, there's a lot of work involved in demolition, and that generated a huge amount of demolition waste. And at the time when we picked up on this idea, we were generating, or we collected over 2,500 tons of waste concrete demolition. So by that initial site visit led to us creating our own batch of recycled concrete. And what you see there is the amount of recycled aggregate that we've generated from our project. And the great thing with the relationship is that we said, look, the great tagline here is if we can take a €100 piece of structure that is now being demolished, and you take it and you generate this new material, recycled aggregate that can then be mixed in and made into new concrete, we want that back into our project. So that completes a beautiful circularity story for us. So that happened quite quickly. So the visit was in late July, August, and by December, we were batching that same recycled aggregate back into our projects. So this image here shows us at the penultimate level on one of our Woodwharf projects with the recycled aggregate mix. We also took advantage at the time the update in the BS 8500 with the introduction of tertiary blends, so that involved the limestone filler. So we capitalize on all these latest developments to make it happen on our project. So not just resting on our laurels, we wanted to investigate what could we do further with that aggregate, and we were invited to go and visit New Stark's installation. So New Stark, if you don't know, is a Swiss company, startup, that takes the off gas from biofuel plants. So you can see there the waste gas is captured by a filter that's all funneled through all these amazing pipe works to their container, where they have this amazing gadget that condenses and freezes that gas into a liquid so that they can then containerize it and then ship it to their to a concrete batching plant. So their model is by taking the demolition waste and capturing CO2 and then combining it together, you can then sequester the CO2 taken from that waste gas, and then basically you bake it into the recycled aggregate, and that permanently locks the CO2 in the aggregate, and you can blend that to make concrete, and then you can also from this positively offset carbon. So as you can see here, the grad who came up with that suggestion was had the honor of pushing the button to start the batching plant for creating our first batch of New Stark concrete that finally came back to North Quay to complete that amazing story. So there, this is a live, recent image of North Quay. So, the idea of creating this circularity story of using the false quay concrete that was there for 100 years, going back into our North Quay project, and the idea is that it will last for another 100 years. So this kind of tagline is really, really important, and this story and this messaging needs to be conveyed to developers who don't quite understand the engineering purposes. And this is the kind of playbook that you have to do within a development company to get them excited and interested in embracing these innovative ideas into engineering and design. Another material that we've been investigating and trialing is biochar, and this is quite an interesting material. So we were approached over a year ago about biochar and how that could be used into concrete. So, being an inquisitive engineer, we said, well, how do you make biochar, and what is it, and what's the process? And what it is taking biomass, and in this case, it's wooden waste, coppice, timber, which chimes in with the theme that we've got today. So by taking that mass, biomass, and putting it through a process of pyrolysis, you capture the CO2 in that organic material, which would, if left to biodegrade, would release back into the atmosphere. Pyrolysis suspends that process by converting that material into a charcoal material called biochar. And by grinding it into a powder, you can mix it into concrete. So we challenged that idea and said, well, if you can make it from any biomass, could you potentially make it from Canary Wharf coffee grounds? Because we've, as not just a developer, but we control and manage the entire estate. We have a lot of coffee shops. So we pushed that idea forward. They were happy to take a wheelie bin. They tested it and said, oh, we can make biochar from your coffee grounds. So it's a great idea, and this relationship that we'd have with our supply chain and this engagement is how we can unlock these ideas where people are reserved and holding it back to say, well, look, tell us about it. We can see how we can apply it. So taking this idea forward by saying, look, we can make biochar from our coffee grounds, we've got a perfect project where we can potentially showcase how it can all come together. So this is well on the wharf. And the story behind this is this sculpture piece, this art piece, has been created by the ocean plastic waste that's been collected. And it's been made into this fantastic full-size blue whale breaching out of the water. And it's been on display around the world as a temporary installation. And Canary Wharf, as we do, decided to buy the art piece and give it a permanent home. So the challenge came to me as the engineer to say, oh, can we put it in the dock? And they said, well, where do you want it? Oh, we want it here in the deepest part of the docking in the estate. So it was a real key engineering challenge to try to support this, put it into this prominent location on our estate. So the team that we had was a great team. You know, we all banded together and say, well, look, if we're going to take on this project, we need to think sustainably and use the right materials and, you know, produce a solution that, you know, really fully displays how you can come together and bring, you know, circularity to fruition. So obviously we had the biochar concrete that was used to form the pad foundation to support the frame, and the frame itself was designed and used from reclaimed steel. So that has helped us to keep the embodied carbon of this project really significantly low as possible. And now we've got this beautiful art piece that everybody can come and enjoy, and there's a plaque that gives you the background stories to blend, you know, all that effort and idea to come together. So, you know, it's really, I think, it's come full circle for it to be here at Canary Wharf with this complete story. Moving on to how can we take that idea from using these innovative materials into mainstream? So biochar concrete was a great idea, and it's good that we've done it for an art piece, but, you know, that's a bit of mass concrete. How do you elevate that into structural concrete? So the only way to do this, and I think this chimes in with what Tom has said, is you need to reverse that thinking. You need to think about the source first, and how do you use that source to get you to design and then into construction. So we're going about full-scale testing by using these innovative concretes. So the biochar is one of it. And finding the opportunities to how can we implement full-scale elements and test them. So what you see here is a steel gantry frame, and that was due to the topography of the site. The site wasn't even, it was part of a leftover phase that we haven't constructed, and we bought this phase brought it forward a lot earlier. You may know it, but this is where the new Hunger Game Theatre is going to be opening next week, and this is how we've kind of like incorporated a testing rig by using this steel gantry. So what we've done is because of the variance in levels, we had to build up that level to marry up the ground bearing slab and the intermediate beams underneath to restrain the double height columns. Was a perfect location to introduce a testing frame for us to build in some test slabs. So what you see there is, you know, we've banded together, and this is the key thing. We created a collective. There's 6 consultants working with us, 2 prominent universities, and our supply chain, our contractors, all working together to come up with this strategy. And what you see here is, you know, that idea started as a single bay, and then as more people came in, they said, well, if you're going to go to all that effort, could we do more? So we've created it into 6 bays, into 3 bays, and then we subdivided it further. And what you see on the screen is half of it is a flat slab, and the other half is a metal deck to replicate residential and a commercial floor. And we fully instrumented it with fiber optics, strain gauge, thermocouples, to get the full understanding of how this concrete behaves. The other interesting one here, as you can see, we've also introduced graphene as one of the mixes, and the graphene here in particular was created from old used tires. So that circularity story, you know, really flows through in terms of the ideas and the way in which we want to direct our projects. So all the effort into preparing that has now created this amazing patchwork of different types of concrete and different types of slabs. And the effort, in delivering this is no mean a small feat. Arranging all the people to do the testing, to do the load tests, the arrangement that we've done, we've got a suite of cubes, cylinders, taking their concrete strength, their cylinder tests, and various means of us monitoring it. So we're getting this full insight of how these new mixes are behaving, so that we can then unlock through data and provide that technical assurance to our engineers to say, look, these are how these materials could be designed for our projects. And we're not stopping. Every opportunity that comes, we look for how we can introduce these ideas. So this is another project. So where we were testing suspended slabs, we had the opportunity, and we took the opportunity to instrument deep 2-meter thick slabs to test these novel mixes, to get the understanding of how they also perform in the basement environment, with thermal effects, hydration, to unlock that through collecting data. So our route map, in terms of how we see to unlock the potential of these new materials, is obviously to address the technical aspects. BS Flex 350 is a great framework in which we can try to navigate that to help our consultants. Scalability is a key aspect, because we need to partner with suppliers who have the capabilities, the investment to scale up, because our projects requires a lot of materials. I mean, it's great that these startups are innovating, but to be able to produce it in the time frame that we want, to really hit net zero and work effectively, we've got to partner with people who have the right resources. And contractors are also a fundamental part of this chain. So they need to be familiar and used to the way in which these concrete behave, the workmanship, the quality, the finish, and engaging them is vital to unlocking this route to market. We've also mentioned about insurance. The great thing about Canary Wharf, we have that pull power to say, look, we are innovating, we're doing these R&D initiatives. We want you to be part of this journey. So we've engaged with our insurers. They've been very proactive. They've been really interested in what we've been doing. And they've been giving us really interesting insight to their views, their risks, profiles, the things that they're concerned about, for us to then fine tune and tweak what we're doing. And then obviously, how do we showcase it? So the best way is doing it through our iconic projects, to deliver it in these tall rise, high rise buildings, to show that this is a way in which we can bring it to market. Thank you.
Great, so we'll just go on to Q&A. We are running a tiny bit behind, so I'm going to shorten this a little bit just in case anyone does need to leave on time. Can I invite back Tom and Gillian as well? We'll get started on Q&A. To get going, I look at the iPad. Do we have any questions in the room? Yes? Go on, Ed.
Thank you. What's interesting, I think, about the Canary Wharf Group's work is that you seem as a company to be pushing this stuff forwards in a way that I don't see so widely, but you're a pretty commercial organisation. So I wonder, what is your primary driver? Is it image? Is it help you sell buildings? What exactly is it?
It's everything. So I think personally, as an engineer, everyone is striving to work out this global problem of how do we do things more sustainably, how do we be more considerate in terms of the selection of materials, and how can we unlock those potential into full-scale construction and projects. So I've been very fortunate to be able to interact and be involved in that whole life cycle of the early development of a design through to delivery on site. So having that oversight and the influence and sphere of influence that I have with the supply chain, that engagement piece, it comes from working with consultants and contractors. All consultants want to be able to have an opportunity to showcase what they can do. And it's just offering up that opportunity creates this hub of interest and excitement to really positively do something. So all that, there's those, there's taglines about commercial and things. It's fine. That all comes with it. But doing the right thing, it's very satisfying, and it gives purpose.
I like that. Yes, from the back of the room.
Thanks. If I could just build on Ed's question, though. So we heard earlier today that the bottom line stands in the way of us doing the right thing. Jonathan, it's not standing in your way. How does Canary Wharf Group overcome that imperative that we come up against so often?
Well, hopefully I've shown you the route map that we're trying to do. So that's the strategy that we're trying to deliver. It's not easy because it's about changing mindset. There's a lot of different stakeholders with all different views and challenges, and it's just engaging. The key thing is about engagement, understanding what is important to them, and then seeing how we can work together to address those risks.
Great, thank you. Okay, I've got some questions from our online audience. Tom, one for you. On small projects, C24 tends to be used, even if I specify C16, as the joiners like working with straighter, less knotty timber, with it being a similar cost. Is there anything that structural engineers can do in this room to kind of maybe satisfy the on-site barriers that a lot of our contractors and trades that might experience from actually using the products?
I think the real, I don't doubt that case is frustrating, but I think one of the real barriers that maybe we could focus on as structural engineers is procurement law, and how procurement sort of inhibits the use of homegrown timber. Mm-hmm. But I think it's probably a site-by-site, case-by-case
it's about hearts and minds, isn't it?
Really. Yeah, it's about relationships and fostering a culture where we're comfortable building with C16, and I think that needs to happen construction as well as design.
Yeah, and like we've seen from today, it's our job to take these other stakeholders, like insurers, like supply chain, on that journey, because they're not experts in this field, and that does take trust and relationship building and courage, as we've determined from today. So thank you for that. And Julian, I've got quite a few questions. Structural engineers want to know all about the testing, don't we? Could you explain fire and impact testing a bit more? We've got someone who would love to collaborate with you, so I can.
Good. That's good. Yeah, fire. We didn't test it. I tested it for fire.
What did you do?
It burns.
Right. Okay.
It doesn't pop like bamboo,
okay.
Which is good. That's actually why I tested it. I wanted to know if it popped. The air inside bamboo expands really rapidly and bursts the wall. It doesn't do that. But yeah, I think I was kind of reassured by hempcrete, right? If you look at hempcrete, it's hemp which does burn, but wrapped in lime or surrounded by lime. It doesn't burn at all. It's very good. And so I imagine that if miscanthus ever got to market, it would have some surrounding material like miscanthus lime or hemp lime surrounding it to give it that inherent fire resistance.
Great. And then a follow-up one just on some more technical things. Given how important bundle creation is to the strength, what role do on-site construction skills and QA play in making this a viable solution for the future?
Yeah, that's a really good one. I don't know, actually. I don't know the answer to that question. In my head, I'm thinking, is this something that becomes a product and is manufactured as a product that goes to market? Or is it something, I think I prefer this, which is that, well, maybe it's something that's really simple and really basic. You can go to your local miscanthus farm and you can follow a series of rules and produce your own building element. That's what I like.
That's more the regenerative approach, isn't it?
Get into all of the issues that the question is alluding to, which is
Yeah.
workmanship and quality and regulation. So
Yeah, okay, great. Any other questions in the room? One at the back.
Just a couple more detailed points on your concrete, really. With the CO2 that you're locking into that concrete, does that affect your carbonation rates, first of all? And then the second one was the energy balance with your charring material. How does that affect things? You've got to obviously expend a bit of energy in creating that char. Is that all still going in the right direction, or is this purely R&D and needs some more work?
Okay, so good questions. So carbonation, so concrete through natural process carbonates anyway. So all the new stuff technology is you just fast track that process. The amount of, so the proposal that came to us in terms of using it for our site does require a lot of due diligence. We've done further chemical tests because we rightly said, well, does that have an effect on the steel that's cast into the concrete? So the process of it doesn't adversely affect the reinforcement, which is our concern, and the test proves that it doesn't. And therefore, the amount of carbon that's sequestered in the concrete will eventually be part of the concrete if left naturally anyway. All that it happens is that you artificially carbonate it a lot quicker. And as long as it doesn't have an effect on the reinforcement, there isn't a concern. In terms of the biochar, so I'm not an expert in terms of how they do the process, but how it's been explained to me is that you need a small amount of energy to start it going, but through a chemical reaction, it heats itself.
Okay, thank you very much. We've got maybe one or two more from the room. Any others? One over here.
Thanks for the presentations. This is a question for Tom. Just wondering, in your experience, because people are quite concerned about C16's, I guess, geometric stability and like the tendency to warp, etc. Where does that warping actually come in place within the supply chain? Is it because the timber merchants have left it in the rain for a long time where it's not really meant to be? Or is it like because of the sowing process? And like, is there anything that you think the supply chain can do to sort of increase the geometric stability of C16?
Honestly, the quickest way to solve the problem that I think we're both trying to solve here is to say no. The material is the material. C16s, we're not going to change the structural properties of C16. It is what it is. It's a similar answer to the naughty question, really. It's about learning the material and learning how to design with it so that the warping and the twisting, which is an intrinsic property, is designed in. And we have done this as well. Unfortunately, my colleagues aren't here to back me up with case studies, but there is cases where we hear stories about buildings that are 50, 60, 100 years old, still warping, still twisting. Now, obviously, it's got an anisotropic property where it flexes one way and not the other, and where from the stem a particular bit is being cut from will affect that warping and twisting. But if the question is how do we stop C16 warping, we don't. We design appropriately. Sorry, that's just handing the question back.
It is what it is. Yeah. It is what it is. Okay, that's brilliant. Unfortunately, we're going to have to finish up there. Thank you so much, Tom, Julian and Jonathan, for your fantastic presentations and contributions.